Now we have already studied AM, GM and HM. So if we have n positive numbers, say x1, x2, xn, where each of xi is a positive real number, then their arithmetic mean, which is x1 plus x2 plus xn by n, will always be greater than or equal to their geometric mean, which is x1, x2, xn to the power 1 by n, and always be greater than or equal to their harmonic mean, which is n upon 1 upon x1 plus 1 upon x2 plus 1 upon xn. So arithmetic mean is always greater than or equal to geometric mean and always greater than or equal to harmonic mean, and we get this equality. So AM will be equal to GM and it will be equal to HM if all the numbers are equal. If x1 equals x2 equals xn. So if we know at least one of them is different, then we'll get this strict inequality. But in general, we'll write this as AM is always greater than or equal to GM and will always be greater than or equal to HM. And we're going to prove it using two methods. First, by using induction. Second, by using Jensen's inequality. Now this AM, GM, HM inequality, it is used to find lower and upper bounds of sum and product. So this AM, it is related to sum. And this GM, it is related to product. So once we have those questions where either sum is constant or product is constant, and we need to find minimum or maximum value of an expression, then the first thing that should come to your mind is this AM, GM, HM inequality. So if product is constant, then they'll ask you minimum value of sum. And if sum is constant, they'll ask you maximum value of product. But you should keep this in mind. We can only use AM, GM, HM when the numbers are positive. So it is not valid for negative numbers. If we have two numbers, A and B, two positive numbers, A and B, such that A is less than B, we know their arithmetic mean is A plus B by 2. Their geometric mean is AB to the power 1 by 2 or under root AB, and their harmonic mean is twice AB upon A plus B. All these three means, they'll lie between A and B. So this AM, it will be greater than GM, and will be greater than HM, and B is the highest number. So B will be greater than your AM, and it will be greater than your GM, and it will be greater than your HM, and it will be greater than your smallest number. So all the three means, they'll lie between the two numbers. And generally, AM, GM and HM of positive numbers will lie between the maximum element and the minimum element given in the set of positive numbers. Now also for two numbers, if we multiply their AM and HM, then A plus B by 2 will cancel. So it will be this AB, which is nothing but G square. So for two numbers, their geometric mean square is equal to AH. Then we can write AG and H, they are in GP. And this is valid only for two numbers. If it is more than two numbers, then this result is not valid. Today we'll prove AM, GM and HM inequality for the general case, and we are going to prove it using induction. So we are going to prove arithmetic mean of n positive numbers is always greater than or equal to their geometric mean, and it will always be greater than or equal to their harmonic mean. So if we have n numbers, say x1, x2 and xn, where each of xi is a positive real number, then x1 plus x2 plus xn by n it'll be greater than or equal to x1 into x2 up to xn to the power 1 by n, and will always be greater than or equal to n upon 1 upon x1 plus 1 upon x2 up to 1 upon xn. So this is what we need to prove. Now, first we'll prove arithmetic mean is greater than or equal to geometric mean. And for this proof, first we'll prove a lemma. Now, a lemma is nothing but a small proven statement which is used as a stepping stone to prove a larger or a more significant result. So basically, it is a helping theorem. So in this lemma, what we'll prove is if a1, a2 and an are positive numbers such that their product is equal to 1. So we are assuming a1 into a2 up to an, this product, it is equal to 1. Then the result is a1 plus a2 plus a3 up to an will always be greater than or equal to n. And we'll get this equality if and only if a1 equals a2 equals an and it is equal to 1. Now we'll prove this case by induction. So first step is we'll prove the base case. So let us take a positive number a1 such that the product is 1. So that means a1 is 1. Now this LHS, it is a1 which is 1 and it is always greater than or equal to 1. So that means P1 is true. Now we'll take our inductive case. So our inductive case is we have n numbers a1, a2, an such that a1 into a2 into an it is equal to 1, and we are going to assume that a1 plus a2 plus an will always be greater than or equal to n. Now using this inductive case, we'll need to prove our P n plus 1. Now for P n plus 1, our left hand side is a1 plus a2 plus a3 up to an plus an plus 1, and we'll need to prove it is greater than or equal to n plus 1. Now here what we'll do is without loss of generality, we can say that out of a1, a2, a3, an plus 1, a1 is the maximum element and it is greater than or equal to 1, and a2 is our minimum element which is less than or equal to 1. So if a1 is maximum and greater than 1 and a2 is minimum and less than 1, then we can write a1 minus 1 into 1 minus a2 will be greater than or equal to 0. So from here we can write a1 plus a2 minus 1 minus a1 a2 will always be greater than or equal to 0. Now to prove this result, what we'll do is we'll take n numbers, and these n numbers are a1, a2, a3, a4 up to an plus 1, and we know that from induction this result holds for n numbers, so it'll always be greater than or equal to n. Now what we'll do is we'll add these two inequalities. This is first and this is your second, and if we add them, what will happen? A1, A2 will cancel, so we can write A1 plus A2 plus A3 up to an plus 1 minus 1. It will be greater than or equal to n, or we can write a1 plus a2 up to an plus 1. It is greater than or equal to n plus 1, which is pn plus 1. That means pn plus 1 is true. This proves our result. So we have proved this result that if we have n positive numbers such that their product is equal to 1, then their sum will always be greater than or equal to n. Now we'll prove am is greater than or equal to gm using this lemma. Now using this lemma, we'll prove our theorem, which is if x1, x2, xn are positive real numbers, then x1 plus x2 plus xn whole divided by n will be greater than or equal to x1, x2, xn to the power 1 by n. Now for this, what we'll do is we'll let y equals x1, x2 xn to the power 1 by n, and we'll take n numbers as x1 upon y, x2 upon y, and xn upon y. Now if we take their product will be x1, x2, xn upon y to the power n, which is 1. Then from the previous lemma, we can say that x1 upon y plus x2 upon y up to xn upon y will be greater than or equal to n. Now we can rearrange this as x1 plus x2 up to xn whole divided by n will be greater than or equal to y, and y is nothing but their geometric mean, which is x1, x2, xn to the power 1 by n. So from here we can say arithmetic mean will always be greater than or equal to geometric mean. Now we haven't proved the equality case. Now in this result, we'll have equality when this equation 2 will have equality, and if equation 2 has equality, we can write a1 minus 1 into 1 minus a2 will be equal to 0. That means a1 should be equal to a2 and will be equal to 1. And basically these are the maximum and minimum elements in this result. So that means we can write a1 equals a2 equals an. So each of the number, it must be equal to 1 to have this equality sign. So we'll have equality only when all these numbers are equal to 1. Now here also, equality holds if all the numbers are equal. That means x1 upon y must be equal to x2 upon y. It must be equal to xn upon y. So from here we can say x1 must be equal to x2 must be equal to xn. So we'll get am equal to gm only when all the numbers are equal. Now we'll come to the second part where we need to prove gm is greater than or equal to hm. So here what we'll do is we'll assume n numbers as 1 upon x1, 1 upon x2 and 1 upon xn, and we'll use this result am is greater than or equal to gm. Now am will be 1 upon x1 plus 1 upon x2 up to 1 upon xn by n, and will be greater than or equal to 1 upon x1, x2, xn to the power 1 by n. If we cross multiply, we can write x1, x2, xn to the power 1 by n will be greater than or equal to n upon 1 upon x1 plus 1 upon x2 plus 1 upon xn. That means geometric mean will always be greater than or equal to harmonic mean, and we'll get equality when 1 upon x1 equals 1 upon x2 equals 1 upon xn. That is when x1 equals x2 equals xn. So from here we have proved that arithmetic mean is always greater than or equal to geometric mean and will always be greater than or equal to harmonic mean for any positive real numbers, and we'll get equality when all the numbers are equal. x1 equals x2 equals xn. So this is how you prove AM, GM and HM inequality. We can also prove AM, GM, HM inequality using Jensen's inequality. Now this inequality says if fx is a convex function, then in that case f x1 plus x2 plus xn by n will be less than or equal to fx1 plus fx2 plus fxn divided by n. And if fx is a concave function, this inequality reverses. So then it will be fx1 plus x2 plus xn by n will be greater than or equal to fx1 plus fx2 up to fxn whole divided by n, and we'll get this equality if all the numbers are equal. x1 equals x2 equals xn. Now a convex function is a function where if we take 2 points and draw a line, so this line will either be above or on the curve, and a concave function is a function where if we draw a line, it'll be either on the curve or below the curve. So this is the distinction of a convex and concave function. Now to prove AMG inequality, we'll assume log function. Now we know that this log, it is a concave function. So for these n positive numbers, x1, x2, xn, which are positive real numbers, we can write log x1 plus x2 plus xn whole divided by n will be greater than or equal to log x1 plus log x2 up to log xn whole divided by n. Now this is log x1 plus x2 plus xn by n and will be greater than or equal to, now this is 1 by n log x1 x2 xn. Now this 1 by n will go to the power and log will cancel. So from here we can say x1 plus x2 up to xn by n will be greater than or equal to x1 into x2 into xn to the power 1 by n, which is basically arithmetic mean is always greater than or equal to its geometric mean, and we'll have this equality if all the numbers are equal. So this is the second way to prove AM GM result, and once we have AM GM, then we can prove GM is greater than or equal to HM. So this is how you prove AM GM and HM inequality. So we'll start with the first inequality, and that's your fundamental AM GM and HM inequality. So the very first inequality is AM GM HM inequality. If we have n positive real numbers a1, a2, a3 up to an, where each of these numbers they are positive real numbers, then we can define their arithmetic mean as their sum a1 plus a2 up to an whole divided by n, their geometric mean as their product a1 a2 an to the power 1 by n, and their harmonic mean as n upon 1 upon a1 plus 1 upon a2 up to 1 upon an. Now relationship between the three means is arithmetic mean is always greater than or equal to geometric mean, that is always greater than or equal to harmonic mean for positive real numbers. So for positive real numbers, their arithmetic mean will always be greater than their geometric mean and will always be greater than their harmonic mean. Now here we have two cases. Case 1, we have this equality sign AM, it is equal to GM and will be equal to HM if and only if all the numbers are same. So this equality sign is only possible when all these numbers, they are same. And we have this second condition when at least one AI is unequal to AJ or numbers are distinct. So at least we have one number which is different from all other numbers. In that case, arithmetic mean is always strictly greater than their geometric mean and will be strictly greater than their harmonic mean. Now, since this AM, it is related to sum and GM, it is related to product, you'll find many situations where it will be given that either sum is constant or product is constant. So if sum is constant, they'll ask you to find maximum value of the product. And if product is constant, then they'll ask you minimum value of the sum. So these are some common problems that you'll find in AM, GM and HM inequality. Now this inequality is so fundamental that it is extensively used in every portion of mathematics. Now let us take up some examples. Now the first question is, if A, B, C are three positive real numbers. So we have three positive real numbers. So A, B, C, they are positive real. Then which of the following is or are true? Now this first one is A square plus B square plus C square. It is greater than or equal to BC plus CA plus AB. So for this first one, what we'll do is we'll take three numbers as A square, B square and C square and we'll write their arithmetic geometric mean inequality taking two at a time. So if we take A square and B square, we can write A square plus B square by 2. It is greater than or equal to A square B square to the power 1 by 2, which is simply AB. In the same way, we can write it for B square and C square. So B square plus C square by 2, it is greater than or equal to BC, and C square plus A square by 2, it is greater than or equal to CA. Now, if we add all these three, then in the numerator, we'll have 2 times A square plus B square plus C square whole divided by 2 and will be greater than or equal to AB plus BC plus CA. Now, we can cancel this 2 with 2. So, we'll get this result as A square plus B square plus C square. It is greater than or equal to AB plus BC plus CA. That means this option A is correct. Now this result, it is an important result in mathematics and the version which is mostly used in JEE Advanced is this version. You will be given A square plus B square plus C square and it is equal to AB plus BC plus CA. Now we know that we'll have this equality when AM is equal to GM and AM is equal to GM if and only if numbers are same. So from here we'll get this condition that A must be equal to B, it must be equal to C. So if we have this strict equality, then all three numbers, they'll be same. Another way to solve the same question is, we can write this as A square plus B square plus C square minus AB minus BC and minus CA. Now what we'll do is, we'll multiply and divide everything with 2. So we can write this as 1 by 2 and it will be this 2a square plus 2b square plus 2c square minus 2ab minus 2bc minus 2ca. Now we'll take a square plus b square and 2ab. Then we'll take b square plus c square 2bc and then we'll have a square plus c square minus 2ca. So we can write this as 1 by 2 and here will be this a minus b square plus b minus c square plus c minus a whole square. Now we know that sum of squares is always greater than or equal to 0. So from here again we can write a square plus b square plus c square will be greater than or equal to ab plus bc plus ca, and we'll have this equality sign if each of the squares is 0. That means we'll have this equality sign, that is a square plus b square plus c square, it is equal to ab plus bc plus ca if a is equal to b and b is equal to c. So that's our option A. Now we'll come to this option B. Now option B is direct application of AMGM. So we have three numbers, a cube, b cube and c cube. They are all positive real numbers. We can write the arithmetic mean. So it will be a cube plus b cube plus c cube by 3 will be greater than or equal to their geometric mean. So there will be a cube, b cube, c cube to the power 1 by 3, which is ABC. So we rearrange, we can write a cube plus b cube plus c cube. It is always greater than or equal to 3 times ABC, which means this option B is also correct. Another way to write this is, we know that a cube plus b cube plus c cube minus 3abc, it is a plus b plus c into a square plus b square plus c square minus ab minus bc and minus ca. Now we know that abc are all positive real numbers, so this is a positive real number, and in the first part we have proved that this expression is always greater than or equal to 0. So from here again we can write a cube plus b cube plus c cube, it is greater than or equal to 3abc. Now we'll come to part C. In part C, we are given three products and we have to prove that it is greater than or equal to 8abc. Now here what we'll do is, we'll take three numbers as ABC and we'll write their AMGM, again taking two at a time. So we can write a plus b by 2, it is greater than or equal to under root ab, b plus c by 2, it is greater than or equal to under root bc, and c plus a by 2 is greater than or equal to under root ca. Now we multiply all these three, we can write a plus b into b plus c into c plus a whole divided by 8, and it is greater than or equal to under root a into under root a. So there will be a, in the same way it will be b and c. So we can write it is greater than or equal to abc, or simply a plus b into b plus c into c plus a, it is greater than or equal to 8 abc. That means this option C is also correct. Now this option D is, we need to prove that bc upon a plus ca upon b plus ab upon c, it is greater than or equal to a plus b plus c. Now for this what we'll do is, we'll divide everything with ABC. So we can write 1 upon a square plus 1 upon b square plus 1 upon c square will be greater than or equal to 1 upon bc plus 1 upon ca plus 1 upon ab. So this first inequality, it is equivalent to its second form. Now we'll prove this the way we have proved this first one. So it is same as this first one, but in case of ABC, we are taking 1 upon a, 1 upon b and 1 upon c. So we can write 1 upon a square plus 1 upon b square by 2 will be greater than or equal to their geometric mean, which is 1 upon ab. In the same way, 1 upon b square plus 1 upon c square by 2, it is greater than or equal to 1 upon bc and 1 upon c square plus 1 upon a square by 2. It is greater than or equal to 1 upon ca. Now if we add all these three, we'll get this result. That means this statement D is also correct. So the correct options are A, B, C, D. Let us take another example. Now here the question is, find the maximum value of this expression for x greater than 0. So here x is a positive number. Now our expression is y equals x plus 1 upon x to the power 6 minus x to the power 6 plus 1 upon x to the power 6 minus 2 upon x plus 1 upon x whole cube plus x cube plus 1 upon x cube. Here what we'll do is we'll take this minus 2 with this second expression. So we can write this as minus, and here will be this x to the power 6 plus 1 upon x to the power 6 plus 2, which actually is a square plus b square plus 2ab. So we can write this as y equals x plus 1 upon x whole to the power 6 minus, and here it is x cube plus 1 upon x cube whole square whole divided by x plus 1 upon x whole cube plus x cube plus 1 upon x cube. Now what we'll do is in the numerator we have x plus 1 upon x to the power 6. We'll write this as x plus 1 upon x to the power 3 whole to the power 2. Now this is a square minus b square. So using the formula we can write this as y equals a plus b, and there will be x plus 1 upon x whole cube plus x cube plus 1 upon x cube into a minus b, and that will be x plus 1 upon x whole cube minus x cube minus 1 upon x cube whole divided by x plus 1 upon x whole cube plus x cube plus 1 upon x cube. Now this expression, it gets cancelled. So now we can write this as y equals x plus 1 upon x whole cube minus x cube minus 1 upon x cube. Now this is a plus b whole cube, so there will be a cube plus b cube plus 3a square b plus 3ab square, and then we have this minus x cube minus 1 upon x cube. Now these two, they get cancelled. So this y will be 3 times x plus 1 upon x. Now we have to find minimum value of their sum, and we know that if we multiply them, their product is 1. So their GM will be constant. So here we'll use AM and GM. So if we use AM and GM, we can write x plus 1 upon x by 2. It is greater than or equal to under root of x into 1 by x, which is 1. So we can write this as this x plus 1 by x. It is greater than or equal to 2. Now if x plus 1 upon x is greater than or equal to 2, then this y, it is greater than or equal to 6. So minimum value of this expression will be simply 6. जो क्वेश्चन हम पढ़ेंगे उसका नाम है नेस्बिट्स इनइक्वालिटी, और इनइक्वालिटी कहता है कि अगर हमारे पास 3 पॉजिटिव रियल नंबर्स a, b और c हैं, तो a अपॉन b प्लस c प्लस b अपॉन a प्लस c प्लस c अपॉन a प्लस b का जो वैल्यू आएगा वो हमेशा 3/2 या 3/2 से बड़ा होगा। अब इस क्वेश्चन को सॉल्व करने का पहला तरीका है हमारा सबसे फंडामेंटल इनइक्वालिटी, जिसको हम बोलते हैं AMGM HM इनइक्वालिटी। तो इस क्वेश्चन के लिए हम यूज करेंगे AM HM इनइक्वालिटी। अब ये क्वेश्चन के लिए हम 3 नंबर्स कंसीडर करते हैं, b प्लस सी, a प्लस सी और a प्लस b। अब इनका अगर अरिथमेटिक मीन लिखेंगे तो हम लिखेंगे b प्लस सी प्लस a प्लस सी प्लस a प्लस b डिवाइड बाई 3, और ये बड़ा होगा या बराबर होगा इसके हार्मोनिक मीन से 3 अपॉन 1 अपॉन b प्लस सी प्लस 1 अपॉन a प्लस सी प्लस 1 अपॉन a प्लस b के। अब इस न्यूमरेटर को देखें तो ये 2a प्लस b प्लस c हो जाएगा। तो अपने इसको क्या कर सकते हैं, इसको लिख सकते हैं 2 टाइम्स a प्लस b प्लस c, और ये राइट हैंड साइड के डिनोमिनेटर को यहां मल्टीप्लाई कर देता है। तो इसको लिखेंगे 1 अपॉन b प्लस सी प्लस 1 अपॉन a प्लस सी प्लस 1 अपॉन a प्लस b, और ये बड़ा होगा या बराबर होगा 9 के। अब इस 2 को भी उधर ले जाता है और इस a प्लस b प्लस c को इन तीनों से मल्टीप्लाई कर देता है। तो इसको लिखेंगे a प्लस बी प्लस सी अपॉन बी प्लस सी प्लस a प्लस बी प्लस सी अपॉन a प्लस सी प्लस a प्लस बी प्लस सी अपॉन a प्लस बी एंड दिस इज ग्रेटर देन इक्वल टू 9/2। अब यहां पे इसको दो पार्ट में स्प्लिट करेंगे, a अपॉन बी प्लस सी और b प्लस सी अपॉन बी प्लस सी, जो कि 1 हो जाएगा। तो ये हो गया a अपॉन बी प्लस सी प्लस 1। इसी तरीके से दूसरे वाले को हम लिख सकते हैं b अपॉन a प्लस सी प्लस 1 और ये तीसरा वाला हो गया c अपॉन a प्लस बी प्लस 1 एंड दिस इज ग्रेटर देन इक्वल टू 9/2। तो इसको रीअरेंज करेंगे तो ये हो जाएगा a अपॉन बी प्लस सी प्लस बी अपॉन a प्लस सी प्लस c अपॉन a प्लस बी। दिस इज ग्रेटर देन और इक्वल टू 9/2 minus 3 and 9/2 minus 3 is 3/2 which completes our proof। अब हम देखेंगे हमारा दूसरा प्रूफ जो कि है सब्स्टिट्यूशन। अब सब्स्टिट्यूशन में अपने b प्लस सी को x मान लेते हैं, a प्लस सी को y मान लेते हैं और a प्लस b को z मान लेते हैं। अगर तीनों को ऐड करेंगे तो यहां से हमारे पास आ जाएगा a प्लस b प्लस c और ये हो जाएगा आपका x प्लस y प्लस z डिवाइड बाय 2। अब यहां से अगर a का वैल्यू निकालना है तो b प्लस c को इसमें सब्ट्रैक्ट कर देंगे तो यहां से a हो जाएगा आपका x प्लस y प्लस z अपॉन 2 माइनस x जो कि हो जाएगा y प्लस z माइनस x अपॉन 2। और इसको अगर b प्लस सी से डिवाइड करना है तो x से डिवाइड करेंगे तो ये हो जाएगा a अपॉन b प्लस सी और ये हो गया आपका y प्लस z माइनस x बाय 2x। तो लेफ्ट हैंड साइड में जो एक्सप्रेशन है इसको अगर हम x वाई z के टर्म्स में लिखेंगे तो ये हो जाएगा y प्लस z माइनस x अपॉन 2x प्लस x प्लस z माइनस y अपॉन 2y प्लस x प्लस y माइनस z अपॉन 2z। अब एक काम करते हैं, ये x y और z के टर्म्स को अलग कर लेते हैं और बाकी टर्म्स को अलग लिखते हैं। तो इसको अपने लिख सकते हैं 1/2 ये हो गया y अपॉन x प्लस z अपॉन x प्लस x अपॉन y प्लस z अपॉन y प्लस x अपॉन z प्लस y अपॉन z। तो ये 6 एक्सप्रेशन हो गए और ये हो गया आपका -1/2 -1/2 -1/2 जो कि हो गया आपका -3/2। अब अगर इस एक्सप्रेशन को देखें तो ऊपर हमारे पास 2y है, नीचे भी 2y है, 2z है, नीचे भी 2z है, ऊपर 2x है, नीचे भी 2x है। तो इन सबको मल्टीप्लाई करेंगे तो इसका वैल्यू 1 आएगा। तो क्लियरली हमें पता है कि अगर इसमें हम AMGM यूज करें तो हम इसका मिनिमम वैल्यू निकाल सकते हैं। तो हम क्या करेंगे, साइड में इसका मिनिमम वैल्यू निकालेंगे। तो अगर इसमें AMGM यूज करते हैं तो ये हो जाएगा आपका y अपॉन x प्लस z अपॉन x प्लस x अपॉन y प्लस z अपॉन y प्लस x अपॉन z प्लस y अपॉन z डिवाइड बाई 6 और ये बड़ा है बराबर है इसके ज्योमेट्रिक मीन से जो कि है इनका प्रोडक्ट जो कि 1 है टू द पावर 1/6। अब 6 को इधर ले जाते हैं तो इसका मतलब ये जो y अपॉन x प्लस z अपॉन x प्लस x अपॉन y प्लस z अपॉन y प्लस x अपॉन z प्लस y अपॉन z का जो वैल्यू आएगा वो आएगा आपका 6 या 6 से बड़ा। अगर यहाँ पे सब्स्टिट्यूट करते हैं तो ये बड़ा होगा या बराबर होगा 1/2 इंटू 6 माइनस 3/2। तो ये हो गया 3 माइनस 3/2 मतलब 3/2। तो ये हो गया हमारा दूसरा तरीका इस इनइक्वालिटी को सॉल्व करने का। अब हम चलते हैं हमारे सातवें प्रूफ की तरफ और इसमें हम यूज करेंगे AMGM और सब्स्टिट्यूशन। तो ये बेसिकली है हमारा AMGM और सब्स्टिट्यूशन को यूज करके। तो यहां पे हम मान लेते हैं कि b प्लस सी x है, a प्लस सी y है और a प्लस बी z है। तो ये इनइक्वालिटी को सॉल्व करने की बजाय हम एक दूसरा इनइक्वालिटी सॉल्व करेंगे जो कि है x प्लस जेड अपॉन वाई प्लस y प्लस जेड अपॉन एक्स प्लस x प्लस वाई अपॉन जेड। अगर इसको हम 6 नंबर्स में अलग अलग डिवाइड करेंगे तो हमको पता है इसका ज्योमेट्रिक मीन 1 आएगा। तो इसका अगर अरिथमेटिक मीन देखेंगे तो यहाँ पे इनको हम 6 नंबर्स के जैसे ले रहे हैं, तो इसके अरिथमेटिक मीन में डिवाइड बाई 6 आएगा और ये बड़ा है या बराबर है इसके ज्योमेट्रिक मीन से। अब ये 6 नंबर्स का प्रोडक्ट 1 आएगा, तो इसका जीएम 1 हो गया। तो यहां से हम लिख सकते हैं x प्लस जेड अपॉन वाई प्लस वाई प्लस जेड अपॉन एक्स प्लस एक्स प्लस वाई अपॉन जेड, ये बड़ा है बराबर है 6 के। अब यहां से एक्स वाई जेड का वैल्यू पुट कर देता है। अब यहां पे एक्स प्लस जेड जो आएगा वो आएगा आपका ए प्लस 2b प्लस सी अपॉन वाई, वाई है आपका ए प्लस सी के। इसी तरीके से वाई प्लस जेड हो जाएगा आपका 2a प्लस बी प्लस सी अपॉन बी प्लस सी प्लस एक्स प्लस वाई हो गया आपका ए प्लस बी प्लस 2c अपॉन ए प्लस बी, और ये बड़ा है बराबर है 6 के। अब इसको दो पार्ट में स्प्लिट करते हैं, तो ए प्लस सी अपॉन ए प्लस बी 1 हो गया, तो ये गया 1 प्लस 2 इंटू बी अपॉन ए प्लस। इसी तरीके से ये हो गया 1 प्लस 2 इंटू ए अपॉन बी प्लस सी, और ये हो गया आपका 1 प्लस 2 इंटू सी अपॉन ए प्लस बी, और ये बड़ा है बराबर है 6 के। अब 1 प्लस 1 प्लस 3, 6 माइनस 3 इज 3, और 2 को इधर ले जाएंगे तो डायरेक्टली हमने लिख सकते हैं कि b अपॉन ए प्लस सी प्लस ए अपॉन बी प्लस सी प्लस सी अपॉन ए प्लस बी, ये बड़ा है बराबर है 3/2 के। Now the second inequality is weighted AMGM inequality. So suppose we have n positive real numbers a1, a2, a3 up to an, where each of ai it is a positive real number, and we have n positive rational numbers which are suppose w1, w2, w3 up to wn, and we'll take them as weights of a1, a2, a3 and an. So these wi's, they are positive rational numbers. Then we can write their weighted arithmetic mean as this am star, and it will be w1a1 plus w2a2 up to wnan upon w1 plus w2 up to wn, and we can write their weighted geometric mean as a1 to the power w1, a2 to the power w2 and an to the power wn whole to the power 1 upon w1 plus w2 up to wn. Now let us take an example. Say for example we have three positive real numbers a, b and c. So these a, b and c, they are positive real numbers, and let us consider their weights as 1, 2 and 3. Then we can write their weighted am as 1 into a plus 2 into b plus 3 into c upon 1 plus 2 plus 3, and there will be a plus 2b plus 3c upon 6, and we can write their weighted GM as a to the power 1, b to the power 2, c to the power 3 whole to the power 1 upon 1 plus 2 plus 3, and there will be a b square c cube to the power 1/6. So this is how we write weighted AMs and weighted GMs. Now if we closely look at these weighted AMs and GMs, it simply means that we are considering numbers in which A is taken one time, we have taken this B two times, and we have taken this C three times. So it will be this A, B, B, C, C, C. If we write their arithmetic mean, it will be A plus B plus B plus C plus C plus C whole divided by total numbers is 6. So that will be A plus 2B plus 3C whole divided by 6. So essentially, it is arithmetic mean of 6 numbers rather than 3 numbers. In the same way, if we write their geometric mean, it will be A into B into C into C into C whole to the power 1 by 6, which is A B square C cube to the power 1 by 6. So basically, they are AM and GM of these 6 numbers. Now here the fundamental is, if AM star is weighted AM of these n numbers and GM star is weighted GM of these n numbers, then their weighted arithmetic mean will always be greater than or equal to their weighted geometric mean. So weighted AM is always greater than or equal to weighted GM for n positive real numbers having positive rational weights. And again here we'll have this equality. So this AM star will be equal to GM star if and only if A1 equals A2 equals AN. Now let us take up an example. We are given that X, Y and Z are positive real numbers. So X, Y and Z, they are positive real numbers such that X into Y into Z, it is equal to 32. Then we have to find minimum value of X square plus 4XY plus 4Y square plus 2Z square. Now clearly we know we have to find minimum value of sum, and we are given something of this product X, Y, Z. So we have to use AM and GM. But the problem here is, if we want to multiply these 4 expressions, then we get X square into 4XY into 4Y square into 2Z square, and then we'll have X cube, Y cube and Z square. So we'll get this expression as XY cube into Z square, but we are given that X into Y into Z is constant. So this expression on the geometric mean side, it won't be a constant, so you won't be able to get this minimum value. Now this problem can be resolved if we want to use weighted AM/GM. So what we'll do is, we'll consider 4 numbers as X square, 2XY, 4Y square and Z square, and we'll consider their weights as 1 and 2. Now if you want to write their weighted arithmetic mean, it will be X square plus 2 into 2XY plus 4Y square plus 2Z square upon 1 plus 2 plus 1 plus 2. So their weighted AM will be X square plus 4XY plus 4Y square plus 2Z square whole divided by 6. Now we can write their weighted GM. It will be X square and then 2XY whole square, 4Y square to the power 1, and then Z square whole to the power 1 by 6. Now it will be 2 square into 4, there will be 2 to the power 4, then X square into X square, X to the power 4, Y to the power 4 and Z to the power 4 whole to the power 1 by 6. Now we can write this as 2XYZ whole to the power 4 by 6. Now X into Y into Z is 32. So this is 64 and 64 is 2 to the power 6. So we can write this as 2 to the power 6 whole to the power 1 by 6. I'll cancel. This is 16. We know that weighted AM is always greater than or equal to weighted GM. So from here we can write x square plus 4xy plus 4y square plus 2z square divided by 6 is always greater than or equal to 16. So from here we can write x square plus 4xy plus 4y square plus 2z square is greater than or equal to 16 into 6, and it is 96. So minimum value of this expression is 96. That means the correct option is this option C. Now let us take another example, and it says the minimum value of sum of real numbers a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10, where a is greater than 0. Now we have to find minimum value of this sum, and each of these numbers, they are positive real numbers. So clearly we can use AM and GM. But the problem here is if we multiply the powers of a, it will be a to the power minus 5 into a to the power minus 4 into a to the power minus 3 into a to the power 8 and a to the power 10. Now these negative powers, they come to a to the power minus 12, and these positive powers are a to the power 18. So their GM, it won't be constant, but we have this 3 here. So if we consider this a cube 3 times, then we'll have a to the power minus 18 here, and in that case this GM will be a constant number. So for this question, we'll consider these 6 numbers: a to the power minus 5, a to the power minus 4, a to the power minus 3, 1, a to the power 8 and a to the power 10 with weights 1, 1, 3, 1, 1 and 1. And if we write their weighted AM, it will be a to the power minus 5 plus a to the power minus 4 plus 3, a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10 whole divided by, now this is 3 plus 3, 6 plus 2, 8. And their weighted GM, it will be a to the power minus 5 into a to the power minus 4 into a to the power minus 3 cube into 1 into a to the power 8 into a to the power 10 whole to the power 1 by 8. Now this is a to the power 0, which is 1. So their GM will be 1. Now again we have to use weighted AM and weighted GM. So weighted AM star will be greater than or equal to weighted GM. So we can write a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10 divided by 8. It is greater than or equal to 1, or simply we can write a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10 is always greater than or equal to 8. Therefore, its minimum value is simply 8. That means answer to this question is this option C. Now the third inequality that we'll study is mth power arithmetic mean. So if we have n positive real numbers, say a1, a2, a3 up to an, and they are all positive real numbers, and we have a real number m, then we have 3 cases depending on the value of m. The first case is if m belongs to r minus 0, 1, that is either m is less than 0 or m is greater than 1. In that case, arithmetic mean of mth power of these numbers, which is a1 to the power m plus a2 to the power m up to an to the power m whole divided by n, will be greater than or equal to mth power of their arithmetic mean. So it will be greater than or equal to a1 plus a2 up to an by n whole to the power m. So this is true if m is less than 0 or m is greater than 1. Now we take an example. Say for example, we consider m as 2. Then this left hand side will be a1 square plus a2 square up to an square by n, which is arithmetic mean of their squares and will be greater than equal to square of their arithmetic mean, and which is a1 plus a2 up to an upon n whole square. Now this m, it can be a negative number also. We can take this m as say minus 1 by 2. Then we can write a1 to the power minus 1 by 2 plus a2 to the power minus 1 by 2 up to an to the power minus 1 by 2 by n, and will be greater than or equal to a1 plus a2 up to an by n whole to the power minus 1 by 2. So this is our first case when m is either less than 0 or greater than 1. Now we have the second case when m lies between 0 and 1. So the second case when m lies between 0 and 1, in that case sign of inequality it reverses. So simply we can write a1 to the power m plus a2 to the power m up to an to the power m whole divided by n will be less than or equal to a1 plus a2 plus an upon n whole to the power n. So if m lies between 0 and 1, then the sign of this inequality, it changes. So if we take an example, suppose we consider m as 1 by 3, we can write a1 to the power 1 by 3 plus a2 to the power 1 by 3 up to an to the power 1 by 3 whole divided by n will be less than equal to a1 plus a2 up to an by n whole to the power 1 by 3. And then we have this third and trivial case if m belongs to this set containing 0 and 1. So if m is 0 or m is 1, in that case both the expressions they'll be equal. So we can write a1 to the power m plus a2 to the power m up to an to the power m whole divided by n will be equal to a1 plus a2 up to an by n whole to the power n. So we have this equality when the value of m is either 0 or 1. Now let us take one example. It says prove that under root 1 plus under root 2 up to under root n, it is less than n into under root n plus 1 by 2. So here what we'll do is we'll consider n numbers 1, 2, 3 up to n, and we'll consider their nth power am's using m as 1 by 2. Now since m lies between 0 and 1, we have to use its second form. So we can write 1 to the power 1 by 2 plus 2 to the power 1 by 2 up to n to the power 1 by 2 whole divided by n will be less than. And here we are using this strict inequality because all these numbers, they are distinct, they cannot be equal. So it will be less than square root of their arithmetic mean, which is 1 plus 2 plus 3 up to n whole divided by n to the power 1 by 2. Now we can write this as under root 1 plus under root 2 plus under root 3 up to under root n divided by n, and it will be less than, this is sum of first n natural numbers. So it will be n plus 1 upon 2, and here we have this n to the power 1 by 2. Now this n and n will cancel, so it will be under root of n plus 1 by 2. Now if we rearrange, we can write this as under root 1 plus under root 2 plus under root 3 plus under root n will be less than n into under root of n plus 1 by 2, which is what we need to prove in this question. Now let us take another example, and this is too small. So what I'll do is I'll write the question. Now it says let ABC be three positive real numbers. So we have three positive real numbers ABC they are all greater than 0 such that a plus b plus c is 1, then we have to find minimum value of 1 upon a square plus 1 upon b square plus 1 upon c square. Now here what we'll do is we'll use mth power am for ABC considering m as minus 2. Now we know that a to the power minus 2 plus b to the power minus 2 plus c to the power minus 2 upon 3 will be greater than or equal to a plus b plus c by 3 whole to the power minus 2. Now it is given that a plus b plus c is 1. So it will be 1 upon 3 to the power minus 2, which is 9. So from here we can write 1 upon a square plus 1 upon b square plus 1 upon c square will be greater than or equal to 27. So minimum value of this expression is 27, and that is the answer to this question. Now the fourth inequality that we'll study is power mean inequality. Now before learning this inequality, we must understand power means. If we have n positive real numbers a1, a2, a3 up to an, and they are positive real numbers, and we have a real number k which is unequal to 0, then their power mean mk a1, a2, a3 up to an, it is defined as a1 to the power k plus a2 to the power k up to an to the power k whole divided by n to the power 1 upon k, where k is a real number and it is not equal to 0. To understand this, let us consider power mean of AB if k is 3. Now it will be this a cube plus b cube by 2 whole to the power 1 by 3. So this is how we write power mean of these numbers with the given k. Now the fundamental here is, if we have non-zero real numbers k1 and k2 such that k1 is greater than k2, then mk1 a1 a2 an is always greater than equal to mk2 a1 a2 up to an. So that is the fundamental for power means. So if we have three positive real numbers a, b and c, then we know that 3 is greater than 2 and it is greater than 1. Then we can simply write m3abc will be greater than equal to m2abc and will be greater than equal to m1abc, which simply means a cube plus b cube plus c cube upon 3 to the power 1 by 3, it will be greater than equal to a square plus b square plus c square upon 3 to the power 1 by 2 and will be greater than equal to a plus b plus c by 3. So this is how we are going to use power mean inequality. Now let us take up an example. Say for example, it says if a, b, c are positive real numbers. So we have positive real numbers a, b and c, and we have to prove that 9 a cube plus b cube plus c cube is greater than equal to a plus b plus c whole cube. We can solve this question using mth power am. Here we are going to solve it using power mean inequality. Now we know that M3 ABC will be greater than or equal to M1 ABC. Now M3 ABC is A cube plus B cube plus C cube upon 3 to the power 1 by 3 and will be greater than or equal to A plus B plus C by 3. Now if we take cube both sides, then we can write A cube plus B cube plus C cube upon 3 will be greater than or equal to A plus B plus C whole cube upon 27. Now we can cancel this 3 with 27, so it will be this 9. So if we rearrange, we can write 9 times A cube plus B cube plus C cube will be greater than or equal to A plus B plus C whole cube, which is what we need to prove in this question. Now let us take another example, and here we have to prove that A cube plus B cube plus C cube upon A square plus B square plus C square is greater than or equal to A plus B plus C by 3. Now again for this, we'll take 3 positive real numbers A, B, C, and again we know M3 ABC is greater than or equal to M2 ABC. So we can write A cube plus B cube plus C cube upon 3 to the power 1 by 3 is greater than or equal to A square plus B square plus C square upon 3 to the power 1 by 2. Now if we take square both sides, then we can write A cube plus B cube plus C cube upon 3 to the power 2 by 3 will be greater than or equal to A square plus B square plus C square upon 3. So that's our first inequality relationship. Now we also know that M3 is greater than or equal to M1. So we can write M3 ABC will be greater than or equal to M1 ABC. So it will be this A cube plus B cube plus C cube upon 3 to the power 1 by 3 and will be greater than or equal to A plus B plus C whole divided by 3, and that's our second inequality relationship. Now what we'll do is we'll multiply these two. Now this is A cube plus B cube plus C cube upon 3 to the power 2 by 3 plus 1 by 3. So this part will be 1. So we multiply it, we get A cube plus B cube plus C cube upon 3 and will be greater than or equal to A square plus B square plus C square into A plus B plus C whole divided by 9. Now this 3 and 9 will cancel, and if we rearrange, then we can write A cube plus B cube plus C cube upon A square plus B square plus C square will be greater than or equal to A plus B plus C by 3, which is what we need to prove in this question. Now here the question is, if ABC are 3 positive numbers and ABC square has the greatest value 1 by 64, then which of the following is or are correct? Now we know that for positive numbers A, B and C, we can write A plus B plus C square by 3. It is always greater than or equal to ABC square to the power 1 by 3, or ABC square will always be less than or equal to A plus B plus C square by 3 whole cube. Now this is the greatest value. Now it says its greatest value is 1 by 64. Now if this is the greatest value, we'll have this condition that AM must be equal to GM, and AM is equal to GM if all the numbers are equal. That means A equals B equals C square. So what we'll do is we'll put A as C square and B as C square. So we'll get C to the power 6. It is equal to 1 by 64 value of C is 1 by 2 and value of A and B, they are 1 by 4 each. And that means this option B is correct. Now the question is, if x is greater than 0, then minimum value of x to the power 1000 plus x to the power 900 plus x to the power 90 plus x to the power 6 plus 1996 upon x is. Now we have the sum of positive numbers. Now if we look at powers of x, and if we add all these powers, it will be 1000 plus 900 plus 90 plus 6, so it will be 1996, and we have this 1996 here. So what we'll do is, we'll write x to the power 1000 plus x to the power 900 plus x to the power 90 plus x to the power 6 plus 1 by x plus 1 by x plus 1 by x. We want to write it separately 1996 times. Now when we multiply all these terms, the powers of x, they'll cancel, we'll get this as 1. So their product is constant. So if we need minimum value of sum and product is constant, then basically we have to use AM, GM. So we'll use AM is greater than or equal to GM inequality. Now its arithmetic mean will be x to the power 1000 plus x to the power 900 plus x to the power 90 plus x to the power 6 plus 1996 upon x whole divided by, now number of terms here is 2000, and it should be greater than or equal to their geometric mean. Now if we multiply all these terms, we get x to the power 1996 into 1 upon x to the power 1996, which is 1 to the power 1 upon 2000, so it will be 1. So value of this sum, x to the power 1000 plus x to the power 900 plus x to the power 90 plus x to the power 6 plus 1996 upon x will always be greater than or equal to 2000. So its minimum value will be 2000, and that's your option B. Now in this question we are given that for triangle ABC, 81 plus 144 e to the power 4 plus 16 b to the power 4 plus 9 c to the power 4, it is equal to 144 ABC, then which of the following is correct? So what we'll do is, we'll consider these 4 numbers and we'll write their arithmetic mean, and it will be 81 plus 144 e to the power 4 plus 16 b to the power 4 plus 9 c to the power 4 upon 4, and it will be greater than or equal to their geometric mean, which is 81 into 144 e to the power 4 into 16 b to the power 4 into 9 c to the power 4 whole to the power 1 by 4. Now we simplify this. This is 144 is 12 into 12. So there will be 9 into 16. Now this is equal to 4 to the power 4, 9 to the power 4, a to the power 4, b to the power 4, c to the power 4 to the power 1 by 4. So from here we can write 81 plus 144 a to the power 4 plus 16 b to the power 4 plus 9 c to the power 4 upon 4 will be greater than or equal to 36 ABC, or we can write 81 plus 144 e to the power 4 plus 16 b to the power 4 plus 9 c to the power 4, it is greater than or equal to 144 ABC. But in the question we are given that there is an equality sign, and we know that AM is only equal to GM if and only if all the numbers are equal. That means 81 must be equal to 144 a to the power 4 and it is equal to 16 b to the power 4 that is equal to 9 c to the power 4. So from here we can write this as a to the power 4 equals 9 by 16, b to the power 4 equals 81 by 16 and c to the power 4 equals 9. So from here we'll get a as root 3 by 2, b as 3 by 2 and c as root 3. Now this clearly we can see that a is less than b and is less than c. So sine a will be less than sine b and will be less than sine c, and since sine is an increasing function and all these values they are positive, so it will lie in the first quadrant. So angle A will be less than angle B and will be less than angle C. So that means option A is incorrect and option B is correct. Now if we look at a square plus b square, there will be 3 by 4 plus 9 by 4. Now this is 12 by 4, 3, and which is c square. That means triangle ABC is a right angle triangle. So option D is also correct. So this triangle ABC, it is a right angle triangle and these sides are AB and hypotenuse is C. Now area of this triangle will be half AB and this value is going to be 1 by 2. A is root 3 by 2 and B is 3 by 2. So this value is 3 root 3 divided by 8 and that's your option C. So the correct options are B, C and D. Now the question is, if this equation has 4 positive roots, then the value of A is. Now if it has 4 positive roots, alpha, beta, gamma and delta, then we can write S1 as alpha plus beta plus gamma plus delta and it is equal to 4. And if we take their arithmetic mean, we can write alpha plus beta plus gamma plus delta by 4. It is equal to 1. So their arithmetic mean is 1. If we write their S4 is alpha beta gamma delta and this value it is 1. And if we write their geometric mean will be alpha beta gamma delta to the power 1 by 4, which is also 1. So in this case, arithmetic mean is equal to their geometric mean, which simply means that all the 4 roots they must be equal. So alpha must be equal to beta, must be equal to gamma, and it must be equal to delta, and each of the value is equal to 1. We need to find A, and basically we can write S2 as this cyclic summation alpha beta and it will be equal to A. Now how many terms we have which are of the type alpha into beta? So all these 4 we have to select n into. So it will be simply 4c2. So we'll have 4c2 terms and the product of each term is simply 1. So this value will be simply 6. So value of A is 6 and that is the answer to this question. Now the question is, if A, B, C are positive real numbers, then prove that 1 plus A, 1 plus B, 1 plus C whole to the power 7 is greater than 7 to the power 7, A to the power 4, B to the power 4 and C to the power 4. Now if we look at this left hand side, then we have 1 plus A into 1 plus B into 1 plus C, which we can write as 1 plus A plus B plus C plus AB plus BC plus CA plus ABC. Now there are altogether 8 terms, and if we use AM and GM using all these terms, we'll get 8 and not 7. And what we need is 7 terms. So what we'll do is we can write 1 plus A, 1 plus B and 1 plus C will be strictly greater than A plus B plus C plus AB plus BC plus CA plus ABC. So what we have done is we have dropped this one, and that's how we get this condition at strict inequality. Now what we'll do is we'll divide everything with 7 Now this is arithmetic mean of these 7 numbers. So arithmetic mean is always greater than or equal to the geometric mean. Now in the geometric mean, we'll have a into a into a into a 4 times. So there'll be a to the power 4, b to the power 4, c to the power 4, whole to the power 1 by 7. And considering these two, we can write 1 plus a, 1 plus b into 1 plus c will be greater than 7 into a to the power 4, b to the power 4, c to the power 4 to the power 1 by 7. Now we'll take 7th power. So we can write 1 plus a, 1 plus b, 1 plus c whole to the power 7 will be strictly greater than 7 to the power 7 and a to the power 4, b to the power 4, c to the power 4, which is what we need to prove in this question. Now here the question is, let m be minimum possible value of log to the base 3, 3 to the power y1 plus 3 to the power y2 plus 3 to the power y3, where y1, y2 and y3 are real numbers such that y1 plus y2 plus y3, it is equal to 9. Now we know that log a base x will be an increasing function if a is greater than 1. So in this case, this a is greater than 1. So it will have its minimum value when the value of expression inside log is also minimum. So we are looking at minimum value of 3 to the power y1 plus 3 to the power y2 plus 3 to the power y3. Now we can use AMGM. So we know that arithmetic mean, which is 3 to the power y1 plus 3 to the power y2 plus 3 to the power y3 upon 3 will always be greater than or equal to 3 to the power y1 plus y2 plus y3 whole to the power 1 by 3. Now y1 plus y2 plus y3 is 9. So if we put 9 here, we'll get this as 3 cube 27. So 3 to the power y1 plus 3 to the power y2 plus 3 to the power y3 is always greater than or equal to 3 to the power 4. So its minimum value. So minimum value of 3 to the power y1 plus 3 to the power y2 plus 3 to the power y3 will be 3 to the power 4, and we'll get this minimum value when 3 to the power y1 equals 3 to the power y2 equals 3 to the power y3. Now if we put this minimum value of expression, we'll get this n. So this n will be log 3 to the power 4 base 3. So value of small m is 4. Now for the second part, we are given, let capital M be maximum possible value of log x1, log x2, log x3, where we are given that x1 plus x2 plus x3, it is equal to 9. Now we can write this m as maximum value of log x1, x2, x3 to the base 3. Now again, it is an increasing function, so we need to find maximum value of x1, x2, x3. Now again, we have to use AMGM, so we can write x1 plus x2 plus x3 whole divided by 3. It is greater than or equal to x1, x2, x3 whole to the power 1 by 3. Now this is 9. 9 by 3 is 3. So x1, x2, x3 will always be less than or equal to 3 cube. So maximum possible value of x1, x2, x3, it will be 3 to the power 3, and we'll have this maximum value when x1 equals x2 equals x3. So value of this capital N will be log 3 to the power 3 base 3. So Value of small m is 4 and value of capital M is 3. Now we need to find the value of log small m cube to the base 2 plus log capital M square to the base 3. Now this is log, and m cube is 4 cube, and that will be 2 to the power 6 plus, and this is log 3, and m square, capital M square is 3 square. Now this is 6 plus 2, 8. So answer to this question is simply 8. Now here the question is, let A, B, C, D be positive real numbers such that A plus B plus C plus D is equal to 11. If the maximum value of a to the power 5, b cube, c square, d is 3750 beta, then the value of beta is. Now what we'll do is, since we need a to the power 5, so we can write this as 5 into a by 5. For b cube, we'll write 3 b by 3 plus 2c by 2 plus d, and we'll take their weighted arithmetic mean. So their weight will be 5 plus 3 plus 2 plus 1, and will always be greater than or equal to their weighted geometric mean, which is a by 5 to the power 5, b by 3 to the power 3, c by 2 square into d whole to the power 1 by, now 5 plus 3, 8, 8 plus 3, 11. So we can write a plus b plus c plus d by 11 will be greater than or equal to a to the power 5, b cube, c square, d to the power 1 by 11 upon 5 to the power 5, 3 cube, 2 square into 1 to the power 1 by 11. Now we are given that a plus b plus c plus d is 11. So this 11 by 11 will be 1. So we can write this as 1. And if we cross multiply, we can write a to the power 5, b cube, c square, d will always be less than or equal to 5 to the power 5, 3 cube into 2 square. So maximum value of this expression is 5 to the power 5, 3 cube into 2 square. Now it says its maximum value is 3750 beta. So we can write 3750 beta will be equal to 5 to the power 5 into 3 cube into 2 square. Now this is 25, 5, and it'll be this 5 cube. We can again cancel it with 25. So it'll be 6, and this is 5, and we can cancel 6 also. So we can write this beta as 5 into 3 square into 2, which is 90. So value of beta in this case is 90, and that is the answer to this question. Now there'll be many questions where you'll need to study the interaction between AP, GP, and HP, and such class of problems would require you to study the interaction between the properties of these three progressions. Now the question is, a GP and HP have same pth, qth, and rth term ABC, show that A into B minus C log A plus B into C minus A log B plus C into A minus B log C, it is equal to 0. Now it says ABC are pth, qth, and rth term of an HP. So that means 1 upon A, 1 upon B, and 1 upon C are pth, qth, and rth term for an AP. Now we can write this as A plus P minus 1D, it is equal to 1 by A plus Q minus 1D, it is 1 by B, and A plus R minus 1 into D is 1 by C. Now if we subtract these two, we can write P minus Q into D, it is equal to 1 upon A minus 1 upon B, and the same way if we subtract these two, we can write Q minus RD equals 1 upon B minus 1 upon C. Now we are also given that ABC are pth, qth, and rth term for a GP. So we can write this A as some A dash r to the power p minus 1, b as sum a dash r to the power q minus 1, and c as sum a dash r to the power r minus 1. And if we take log, we can write log a equals log a dash plus p minus 1 log r log b, and this log a dash plus q minus 1 into log r, and log c equals log a dash plus r minus 1 into log r. So we'll take everything as log. Now if we subtract these two, we can write log a minus log b, it is equal to p minus q into log r, and from second and third we can write log b minus log c as q minus r into log r. Now we'll come back to this first one. If we divide these two, we can write p minus q upon q minus r, it will be equal to b minus a upon ab into c minus b to bc, which is b minus ac upon a into c minus b. And if we divide these two, we can write log a minus log b upon log b minus log c will be equal to p minus q upon q minus r. Now if we equate these two, we can write c into b minus a upon a into c minus b will be equal to log a minus log b upon log b minus log c. Now we cross multiply, we can write c b minus a log b minus c b minus a log c will be equal to a c minus b log a minus a c minus b log b. Now we'll take everything on the left hand side. Then we can write this as a b minus c log a, now plus, and we take log b on the left hand side, it will be bc minus ac and ac minus ab. So there will be b c minus a log b, and this is plus, we'll take this plus sign, so it will be c into a minus b log c equals 0, which is what we need to prove in this question. Now here the question is given that a to the power x equals b to the power y equals c to the power z equals d to the power u, where a, b, c, d are in GP, then show that x, y, z, u are in HP. Now what we'll do is we'll take this as lambda. Then if we take log, we can write x log a equals y log b equals z log c equals u log d equals log lambda, or log a equals log lambda upon x, log b equals log lambda upon y, log c equals log lambda upon z, and log d equals log lambda upon u. Now in the question it says a, b, c, d, they are in GP. Now we know that if a, b, c are in GP, then log a, log b, log c, and log d, they are in AP. Now we'll put the value of log a, log b, log c, and log d. So there will be log lambda upon x, log lambda upon y, log lambda upon z, n log lambda upon u. It will also be an AP. Now we'll divide everything with log lambda, and we know that if we divide each term with a constant, then it will still remain an AP. So that means this 1 upon x, 1 upon y, 1 upon z, and 1 upon u will be an AP, and reciprocal of an AP is HP. So that means x, y, z, u, they are in HP, and which is what we need to prove in this question. Now the question is, find three numbers A, B, C between 2 and 18. So we have to find these three numbers A, B, C lying between 2 and 18 such that their sum is 25. So that means A plus B plus C is 25. And then it says the numbers 2A and B are consecutive terms of an AP. So that means 2A equals 2 plus B. And then it says B, C and 18 are consecutive terms of a GP. So that means C square equals 18B. Now what we'll do is, we'll put the value of A in this equation. We'll multiply it with 2. So we'll get 2A plus 2B plus 2C equals 50. And 2A is B plus 2. So there will be 3B plus 2C equals 48. And we know that 18B is C square. So what we'll do is we'll multiply everything with 6. So it will be this 18B plus 12C, and this is equal to 48 into 6, which is 288. Now this 18B is C square, so we can write C square plus 12C minus 288 is equal to 0. Now 288 is 6 into 48, which is 6 into 8 into 6. So we can write this as C square plus 24C minus 12C minus 288 equals 0. So from here we get C plus 24 and C minus 12 equals 0. So the only positive value of C in this case is C equals 12, as A, B, C lie between 2 and 18. Now once C is 12, B is C square by 18. So there will be 12 into 12 divided by 18. Value of B is 8. And once we have B and C, B plus C is 20. Then the value of A is 5. So we get A as 5, B as 8, and C as 12. Now in this first question it says value of x plus yz is 15 if A, x, y, z and B are in AP. So it says value of x plus y plus z, it is 15 if A, x, y, z and B, they are in AP. Now we know that in an AP, arithmetic mean of terms equidistant from beginning and end, it is equal. That means A plus B by 2, it is equal to x plus z upon 2, and it is equal to y. So in this x plus z will be equal to A plus B, and this y is A plus B by 2, and this is equal to 15. So from here we can write value of A plus B is 10, and that's our first equation. Now in the second part it says if 1 by x plus 1 by y plus 1 by z equals 5 by 3, and if A, x, y, z and B, they are in HP, find the value of A and B. Now if they are in HP, then 1 upon A, 1 upon x, 1 upon y, 1 upon z and 1 upon B, they are in AP. That means again arithmetic mean of terms equidistant from beginning and end will be same. So 1 upon A plus 1 upon B by 2 must be equal to 1 upon x plus 1 upon z by 2 and will be equal to 1 upon y. Now this is 1 upon a plus 1 upon b, and this is 1 upon a plus 1 upon b whole divided by 2. So it will be this 3 by 2 times 1 upon a plus 1 upon b, and that will be equal to 5 by 3. Now we can write this as 3 by 2 a plus b upon ab, and this is equal to 5 by 3. Now we already know a plus b is 10. So if we put a plus b as 10, we can write this as 3 by 2. This is 10 upon AB, and this is equal to 5 by 3. Now I'll cancel. We'll get value of A into B as 9. So A into B is 9 and A plus B is 10. Now two equations, two unknowns. Now you put the value of B, we can write A plus 9 upon A equals 10, or A square minus 10A plus 9 equals 0. We get A minus 1, A minus 9 equals 0. So either the value of A is 1 or value of A is 9. And if A is 1, value of B is 9. And if A is 9, value of B is 1. And this is the answer to this question. Now this B question is the value of XYZ. It is 15 by 2 if A, X, Y, Z and B, they are in AP, and this X, Y, Z is 18 by 5 if A, X, Y, Z and B, they are in HP. We have to find the value of A and B, assuming them to be positive integers. Now we'll take this first case when A, X, Y, Z and B, they are in AP. Now common difference of this AP will be simply B minus A upon 4. So this X will be simply A plus D. So it will be this A plus B minus A by 4, which is 3A plus B by 4. Y is X plus D. So it will be 2A plus B by 4, and Z will be Y plus D, which is A plus 3B by 4. So if we multiply X, Y and Z, we'll get 3A plus B into 2 times A plus B into A plus 3B upon 64. It is equal to 15 by 2, and this divided by 32. Now it says if A, X, Y, Z and B, they are in HP, then X into Y into Z, it is 18 by 5. Now if A, X, Y, Z and B, they are in HP, then 1 upon A, 1 upon X, 1 upon Y and 1 upon Z. So it will be same as this first equation where A, X, Y, Z, B, they are in AP. The only difference is here A is 1 upon A, B is 1 upon B, X is 1 upon X, Y is 1 upon Y and Z is 1 upon Z. So here we'll get 1 upon X into 1 upon Y into 1 upon Z as this 3 upon A plus 1 upon B, 1 upon A plus 1 upon B and 1 upon A plus 3 upon B by 32, and it will be equal to 5 by 18. So we can write this as 3B plus A into A plus B into B plus 3A upon 32, and this is AB cube will be equal to 5 by 18. Now we know that this 3A plus B a plus 3b upon 32, it is equal to 15 by 2. So we'll replace this value here with 15 by 2. So we can write 15 by 2 ab cube will be equal to 5 by 18. Now this is 9, this is 3, so we'll get ab cube equals 27, or the value of AB is 3. Now it says A and B are positive integers. So if A and B are positive integers, the only solutions we'll get is either A is 1 and B is 3, or A is 3 and B is 1. Now here the question is, if one AMA and two GMs P and Q be inserted between two given numbers, then show that PQ plus QQ is equal to 2APQ. Now let the two numbers be X and Y. Now it says we have inserted one AMA between X and Y. So basically this A will be X plus Y by 2. And we have inserted two GMs P and Q between X and Y. Now its common ratio R will be simply Y by X to the power 1 by 3. So this P, it will be X into R, which is X to the power 2 by 3 into Y to the power 1 by 3, and Q, it will be P into R, which is X to the power 1 by 3 into Y to the power 2 by 3. So now we have PQ and we also have A. Now it says we need to find PQ plus QQ. Now if we take their cube, we can write this is X square Y and this is XY square. So we can take XY common and then it will be this X plus Y. Now we multiply P and Q, it will be X to the power 2 by 3 into X to the power 1 by 3, which is simply X. In the same way, it is Y to the power 1 by 3 into Y to the power 2 by 3, which is Y. So we can write this XY as PQ, and we know that X plus Y is nothing but 2A. So it will be this 2A into PQ, which is what we need to prove in this question. Now here the question is, given a 3-digit number whose digits are 3 successive terms of a GP. Now suppose 3-digit number is XYZ, and here I'm just writing their digits. So this is units digit, this is tens digit, and this is hundreds digit, and they are in GP. So that means we have Y square equals XZ, and that's our first equation. Now it says if we subtract 792 from it, we'll get a number written by same digits in the reverse order. Now if we subtract 792 from it, we'll get the same number in reverse order. So there'll be ZYX. Now actual way of writing it will be, the number is 100x plus 10y plus z, and we are subtracting 700 plus 90 plus 2, and that will be equal to 100z plus 10y plus x. Now this 10y and 10y will cancel, so we can write 99x minus 99z, and that will be equal to 792, and this is 99x minus z, and we can write this as 11 into 72. Now this is 9 and this is 8. So the second equation we get is x minus z equals 8. Now it says if we subtract 4 from 100th digit of the initial number and leave the other digits unchanged, we get a number whose digits are successive terms of an AP. So we subtract 4 from this 100 number. So x minus 4, y and z. Now it says they are in AP. So that means 2y equals x plus z minus 4. Now since we have 3 equations and 3 unknowns, we should be able to find the value of x, y and z. Now we need to find the value of x, y and z. So what we'll do is we'll write z as x minus 8, and if we put z as x minus 8 here, we'll get 2y equals 2x minus 12, or y equals x minus 6, and then we'll put the value of y and z in this equation. So we'll get x minus 6 whole square equals x into x minus 8, which is x square minus 12x plus 36, and that will be equal to x square minus 8x. Now this x square will cancel, so we'll get 4x equals 36. Value of x is 9. So we have our x and the value of x is 9. Now if we put x as 9, we get y as 9 minus 6. So y will be 3 and z is 9 minus 8. So z is 1. So this number will be 931. And that is the answer to this question. Now the question is, if ax square plus 2bx plus c equals to 0 and a1x square plus 2b1x plus c1 equals to 0 have a common root. So they both have a common root, and it also says a upon a1, b upon b1 and c upon c1, they are in AP. Then show that a1, b1, c1, it is in GP. Now the first thought in this question is to find condition of common root and then maybe try this AP condition to prove that a1, b1, c1, they are in GP. But this method, it proves to be very lengthy. So what we'll do is we'll say these three numbers, they are in AP, and let these numbers be k minus d, k and k plus d. So that means a upon a1 is k minus d, b upon b1 is k, and c upon c1 is k plus d, or we can write a as k minus d into a1, b as k into b1, and c as k plus d into c1. Now if we put it in this equation, we can write this equation as k minus d a1 x square plus 2 k b1x plus k plus d c1 equals to 0. Now we'll take terms of k together, so we can write k, and this is a1 x square plus 2b1x plus c1, and then we'll take terms of d together, so it'll be this minus d, and then we'll have a1 x square minus c1 equals 0. Now let the common root for both the equations be alpha. So if alpha is common root, then we can write a alpha square plus 2b alpha plus c equals to 0, and then a1 alpha square plus 2b1 alpha plus c1 equals to 0. Now alpha is common root, so we'll put x is alpha, we can write k, and this is a1 alpha square plus 2b1 alpha plus c1 and minus d, and here will be this a1 alpha square minus c1 equals 0. Now we know that a1 alpha square plus 2b1 alpha plus c1, it is 0. So this value will be 0. So from here the condition that we get is a1 alpha square minus c1 equals to 0, or alpha square is c1 by a1, that is alpha is under root c1 by a1. Now alpha is common root of both the equations. So alpha is going to be the root of the equation a1x square plus 2b1x plus c1 equals to 0. So we'll put the value of alpha here. So we'll get a1 c1 upon a1 plus 2b1, and here will be under root of c1 upon a1 and plus c1 equals to 0. Now I'll cancel, and we may have a plus sign or a minus sign here, so it will be this plus minus. So from here we can write plus minus 2b1 under root c1 upon a1 will be equal to minus 2c1. Now this 2 and 2 will cancel, so you get plus minus b1 equals minus under root of a1 c1, or simply we can write b1 square equals a1 into c1, which means a1 b1 c1, they are in GP, which is what we need to prove in this question. In most of the exams you'll find this question other way around. So what generally they do is they'll give you this equation ax square plus 2bx plus c equals to 0, and this other equation a1x square plus 2b1x plus c1 equals to 0, and then they'll say they have a common root, and then they'll give the condition that a1 b1 c1, they are in GP, and then they'll ask you find a upon a1, b upon b1 and c upon c1, they are in what. So when the question is given like that, we know that for this second equation a1 b1 c1, they are in GP, that means b1 square equals a1 c1. Now if we find discriminant for this equation, there will be 4b1 square minus 4a1 c1, there will be 0. So it simply means that roots of this equation are equal. So this equation will have two equal roots, alpha and alpha. Now if we write sum of roots, we can write 2 alpha equals minus 2 b1 upon a1. So from here we get alpha as minus b1 upon a1. Now since alpha is going to be the common root, it is going to satisfy this first equation. So we'll put the value of alpha in this first equation. So we'll get a, and here will be this b1 upon a1 whole square, and then it will be this minus 2b b1 upon a1 plus c equals 0, and we are going to divide everything with b1 square. So we can write a upon a1 square minus 2b a1 b1 plus c upon b1 square equals 0. Now we know that b square is a1 c1. So we'll write this b1 square as a1 c1. So we'll get a upon a1 square minus 2b a1 b1 and plus c upon a1 c1 equals to 0. We'll take a1 common. So from here we'll get this condition that twice b upon b1 equals a upon a1 plus c upon c1, which means a upon a1
B upon B1 and C upon C1, they are in AP. So this is how we prove that A upon A1, B upon B1 and C upon C1, they are in AP. And at times they may ask you A1 upon A, B1 upon B and C1 upon C. So if they are in AP, then their reciprocals, they will be in HP. Now here the question is, if A, B, C, D and E be 5 numbers such that A, B, C, they are in AP, B, C, D, they are in GP, and C, D and E, they are in HP, that says prove that A, C and E, they are in GP. Now condition of an AP is B equals A plus C by 2. Here C square will be equal to B into D, and here D is equal to 2CE upon C plus E. Now first is we have to prove that A, C and E are in GP. So for this first one, we have to relate A, C and E. So for this, what we'll do is we'll take this third one and multiply it with B. So we'll get BD equals twice CE upon C plus E into B. Now B into D is C square. So it will be the C square and then 2CE upon C plus E, and this B is A plus C by 2. Now this 2 will cancel. This C will cancel. So we get C square plus EC, and that will be equal to AE plus EC. Now EC will cancel. So from here we can say C square equals AE, or AC and E, they are in GP. So that's our first part. Now the second part says prove that E equals 2B minus A whole square upon A. So we have to find E in terms of A and B. So for the second one, we have to find E in terms of A and B. Now from here we can write C equals 2B minus A, and if we put C here, we can write D as 2B minus A whole square upon B, and this D is also equal to 2CE upon C plus E. So this 2, and we'll replace C with B minus A, 2B minus A. So it will be this 2B minus A into E upon 2B minus A plus E. Now this 2B minus A will cancel. We can write this as 2B minus A whole square plus 2B minus A into E, and that will be equal to 2BE. Now 2B into E will cancel. So we'll get A into E as 2B minus A whole square, or E is 2B minus A whole square upon A. Now this third part is, if A is 2 and E is 18, find the value of B, C and D. Now we'll put E as 18, then we'll get 2B and A is 2, 2B minus 2 whole square upon, and A is 2, so we'll get 2B minus 2 equals root 36, which is plus or minus 6, or B minus 1 equals plus or minus 3. So if we take plus sign, we'll get B as 4, and if we take minus sign, we'll get B as minus 2. Now C is 2B minus A. We want to write C. So this C, it will be 2B minus A. Now if B is 4, then C is 8 minus 2, 6. And here if B is minus 2, it will be minus 4 minus 2. then value of c is minus 6. And now we have to find the value of d. And we know that d is twice ce upon e plus c. So here this d will be 2, 6 into 18 upon 24. So this is 2. So value of d is 9. So value of b, c and d, it can be 4, 6, 9. And here it will be this 2, c is minus 6, e is 18, and then e plus c is 12. So it will be minus 18, or it will be minus 2, minus 6 and minus 18. And that is the answer to this question. Now here the question is, an AP, a GP and an HP have A and B for the first two terms. Then show that their n plus 2th term will be in GP if it is this given condition. Now, if we talk about this AP, we know that first two terms are A and B. So its common difference will be B minus A, and then its n plus 2th term will be A plus n plus 1 into D, which is A plus n plus 1 into B minus A. We can write as n plus 1 B minus NA, and that's our first result. Now for this GP, first two terms are again A and B. So in this case, common ratio is B by A. So its n plus 2th term will be A, and this is R to the power n plus 1. So it will be this B to the power n plus 1 upon A to the power n. And for this HP, first two terms are A and B. So its corresponding AP will be 1 upon A, 1 upon B. So its common difference is 1 upon B minus 1 upon A. And for this corresponding AP, its n plus 2th term is 1 upon A plus n plus 1 into 1 upon B minus 1 upon A, which is n plus 1 upon B minus NA, or we can write n plus 1A minus NB upon AB. Now for this HP, corresponding term will be AB upon n plus 1A minus n into B. Now we have these three terms, and it says these three terms, they are in GP. So if these three terms, they are in GP, we can write G n plus 2 square, and will be equal to A n plus 2 into H n plus 2. Now this G square will be B to the power 2n plus 2 upon A to the power 2n, and this A n plus 2 is n plus 1b minus na into, and this H is AB upon n plus 1a minus n to b. Now this b will cancel once, so it will be this 2n plus 1, and we'll take this a also, so it will be this 2n plus 1. So we can write b to the power 2n plus 1 upon a to the power 2n plus 1, it is equal to n plus 1b minus na upon n plus 1a minus n into b. What we'll do is we'll cross multiply. So we can write n plus 1 a b to the power 2n plus 1 minus n b to the power 2n plus 2, and it will be equal to n plus 1 b into a to the power 2n plus 1 and minus n a to the power 2n plus 2. Now we'll take terms of n plus 1 together and n together. So we can write n plus 1, and here we'll take ab common. So if we take ab common, we'll get b to the power 2n minus a to the power 2n, and here will be this n b to the power 2n plus 2 minus a to the power 2n plus 2. Now we need n plus 1 upon n. So we can rewrite this as n plus 1 upon n as b to the power 2n plus 2 minus a to the power 2n plus 2 upon ab into b to the power 2n minus a to the power 2n, which is what we need to prove in this question. Now in this question it is given that x, y, z are in GP, and here it should be x is greater than 1 and not x equal to 1. So it says x, y, z, they are in GP, and we know that if x, y, z are in GP, then log x, log y, and log z, they'll be in AP. Now, if we add a constant number to each of the terms, then it will still remain an AP. So 1 plus log x, 1 plus log y, and 1 plus log z will be an AP. And if we take the reciprocal, it will be 1 upon 1 plus log x, 1 upon 1 plus log y, 1 upon 1 plus log z. Now reciprocal of an AP is HP. So these three terms, they are in HP. That means correct option is this option B. Now the question is solve the following equations for x and y. Now we are given that log x base 2, log x base 4, log x base 16, it is equal to y. Now this 4 is 2 square, 16 is 2 to the power 4, and we know that power of base comes as reciprocal. So it will be this log x base 2, it will be this 1 by 2, log x base 2, it is 1 by 4, log x base 2, and this is equal to y. We take log x base 2 common, and then we are left with this infinite GP, 1 plus 1 by 2 plus 1 by 4 up to infinite, which is log x base 2, and this is a upon 1 minus r. So it will be this 2 log x base 2. So that's your y answer, first equation. Now we are given that 5 plus 9 plus 13 up to 4y plus 1, and this is 1 plus 3 plus 5 up to 2y minus 1, and this is equal to 4 log x base 4. Now this first sequence, it is an AP with common difference of 4 and number of terms y. So its sum will be y by 2 a plus l, which is 5 plus 4y plus 1, and here it is sum of first odd numbers and total number of numbers is y. So it will be simply y square, and here we can write this 4 as 2 square, so it will be this 2 log x base 2. Now we know that 2 log x base 2 is nothing but y, so we'll write this as y. Now here y and y will cancel, so we can write 2y plus 3 equals y square, or y square minus 2y plus 3 equals 0. We can write y minus 3, y plus 1 equals to 0, value of y is 3. Now since y is also number of terms, it cannot be negative. So the only value of y we are taking is y equals 3 and not y equals minus 1. So if we take y as 3, then log x base 2 is 3 by 2, then x is 2 to the power 3 by 2, which is simply 2 root 2. So value of x is 2 root 2 and value of y is 3. Now here the question is, suppose a, b, c are in AP, that means twice b equals a plus c, and a square, b square, c square are in GP. That means b square square is equal to a square into c square, or b square equals plus or minus ac. And it is given that a is less than b is less than c, and a plus b plus c is 3 by 2. Find the value of a. Now A plus C is 2B. So we put A plus C as 2B, we get B as 1 by 2. And if B is 1 by 2, we write A into C as plus or minus 1 by 4. And if we put B as 1 here, we get A plus C as 1. So we can write A and the C is plus minus 1 by 4. So it will be plus minus 1 by 4A and it is equal to 1. So we can write 4A square minus 4A plus minus 1 equals 0. And if we add 1 and subtract 1, we can write 2A minus 1 whole square equals 1 plus or minus 1. Now, if we take this minus sign, we'll get A as 1 by 2, which is same as B, which is not possible. So we'll need to take this plus sign, and if we take this plus sign, we get 2A minus 1 whole square. It is equal to 2, or 2A minus 1 equals plus or minus root 2. So this A, it will be 1 by 2 plus minus, now root 2 upon 2 is 1 by root 2. Now since this A, it has to be less than 1 by 2, the only value of A possible here is A equals 1 by 2 minus 1 upon root 2, and that's your option D. Now the question is, let AB be positive real numbers such that A, A1, A2 and B, they are in AP. Now common differences, B minus A upon 3. So this A1 will be A plus B minus A upon 3. So it will be 2A plus B upon 3. And in the same way, A2 will be A plus 2B upon 3. So we have A1 and A2. Now it says A, G1, G2 and B, they are in GP. So for this question, it should be G1, G2. Now here, R will be B upon A to the power 1 by 3. So this G1, it will be A to the power 2 by 3, B to the power 1 by 3, and G2 will be A to the power 1 by 3 and B to the power 2 by 3. And this third one is A, H1, H2 and B, they are in HP. Now this is same as this first one because it's corresponding 1 upon A, 1 upon H1, 1 upon H2, 1 upon B. They'll be in AP, and for this AP we are going to use 1 upon A and 1 upon B, but we have to take the reciprocals. So for this we are going to write H1 as 3 upon 2 upon A plus 1 upon B, that is 3AB upon 2B plus A, and H2 will be 3AB upon 2A plus B. So now we have A1, A2, G1, G2 and H1, H2. Now this first part is G1, G2 upon H1, H2. So we multiply them, we can write G1, G2 upon H1, H2. Now G1, G2 is product of these two terms. Now A to the power 2 by 3 into A to the power 1 by 3 is A, and B to the power 1 by 3 and B to the power 2 by 3 is B. So it will be simply AB upon H1, H2. Now this is 3AB upon A plus 2B, and this is 3AB upon B plus 2A. Now this AB and AB will cancel, so it will be equal to A plus 2B into B plus 2A upon 9AB, which is this right hand side. Now we'll also need to prove that A1 plus A2 upon H1 plus H2 is also equal to this same result. So if we take A1 plus A2, A1 plus A2, it will be 2a plus b, and this is a plus 2b, which is 3a plus 3b upon 3. So it will be nothing but a plus b. And then if we write h1 plus h2, we'll take 3ab common, and then it will be 1 upon 2b plus a plus 1 upon 2a plus b. So it will be this 3ab, and this is 3 times a plus b upon 2b plus a and 2a plus b. Now if we divide them, we can write a1 plus a2 upon h1 plus h2. There will be a plus b upon 9ab a plus b into a plus 2b into b plus 2a. Now this a plus b will cancel, and this is what we need to prove in this question. Right, the question is, if a, b, c are in AP and a square, b square, c square are in HP, then prove that either a equals b equals c or ab minus c by 2 form a GP. Now in this case it says a, b, c, they are in AP, that means b minus a is equal to c minus b, and let it be equal to d, which is its common difference, and a square, b square, c square, they are in HP, which means 1 upon a square, 1 upon b square, and 1 upon c square, they are in AP. So you can write 1 upon b square minus 1 upon a square will be equal to 1 upon c square minus 1 upon b square. Now this is a square minus b square upon a square b square will be equal to b square minus c square upon b square c square. Now here b square will cancel, so we can write a plus b into a minus b upon a square will be equal to b plus c into b minus c upon c square. Now a minus b is minus d and b minus c is minus d. So this is minus d and this is minus d. So if we cancel this out, we'll get this one result that d is 0. And if d is 0, it means a equals b equals c. So one of the results that we can get here is a equals b equals c. Now if we consider d is unequal to 0, then we can write a plus b upon a square will be equal to b plus c upon c square. So ac square plus bc square will be equal to a square b plus ca square. Now we'll take terms of ac together, so it will be this ac into c minus a, and it will be equal to b into a square minus c square. Now a is unequal to c because d is unequal to 0. So here we can cancel c minus a, so we can write minus ac, and that will be equal to b a plus c. And since a, b, c are in AP, we can write b equals a plus c by 2 or a plus c as 2b. So it will be this 2b square. So we'll get this condition that 2b square equals minus ac or ab and minus c by 2, they form a GP. So we'll get two conditions, either a equals b equals c or ab minus c by 2 will form a GP. Now the question is, we are given this series SR where R is greater than 0, then which of the following is or are correct? Now we are given that SR is this nested loop under root of R plus under root of R plus under root of R, and will continue up to infinite. Now this also is going to be SR, so we can write SR equals under root of R plus SR or SR square minus SR, it is equal to R. Now if we solve SR, we can write it is going to be 1 plus minus, we'll discard minus because this sum is going to be positive, and it will be under root of 1 plus 4R divided by 2. Now the first option is S2, S6, S12 and S20 are in AP. So if we write S2 will be 1 plus under root of 9 by 2. So there will be 4 by 2. So S2 is 2. S6 will be 1 plus, now this is 25, 5, 6. S6 is 3. S12 is 7 plus 1, 4. And S20 is 9 plus 1, 10, 10 by 5, 5, 2, 3, 4, 5, which is an AP. That means this option A, it is correct. Now for this option B, we need S4, S9 and S16. Now S4 will be 1 plus root 17 by 2. S9 it will be 1 plus root 37 by 2. And S16 it is 1 plus root 65 whole divided by 2, and all three of them are irrational. That means this option B is also correct. For this option C, if we look at 2SR minus 1 whole square, it is a 1 plus 4R, which is a linear term. That means this series 2SR minus 1 whole square, it is an AP. That means these three terms, S3, S4 and S5, they are terms of an AP. So option C is also correct. And option D is S2, S12 and S56. Now we already have S2. S2 is 2. S12 is 4. We need to find S56. Now S56 is 1 plus under root of 1 plus 4 into 56 whole divided by 2. Now 56 into 4 is 224. So it is 225, which is 15. So S56 is 8. So 2, 4 and 8, it is a GP. So that means option D is also correct. So the correct options are A, B, C, D. And the question, it says the numbers A, B, C are between 2 and 18. So we have three numbers A, B and C, and they lie between 2 and 18 such that their sum is 25. So that means A plus B plus C, it is 25. The numbers 2A and B are consecutive terms of an AP. That means twice A equals B plus 2, and the numbers B, C and 18 are consecutive terms of a GP. That means C square equals 18B. We need to find the value of ABC. Now we have three equations and three unknowns. Now first what we'll do is we'll put the value of 2A here. We'll multiply it with 2. So we'll write 2A plus 2B plus 2C equals 50. Now 2A is B plus 2. So there'll be 3B plus 2C equals 48. Now 18B is C square. So we'll multiply this with 6. So we can write 18B plus 12C, and this is 48 into 6, which is 288. Now 18B is C square. So we can write C square plus 12C minus 288 equals 0. Now this is 8 into 6 into 6. So we can write this as C square plus 24C minus 12C minus 288 equals 0. C plus 24 minus 12, and this is C plus 24 equals 0. So from here, the positive value of C we'll get is C equals 12. Once we have the value of C, we can write B. Now this B is C square by 18. So there will be 12 into 12 divided by 18. So value of B is 8. And if we put the value of B and C in this first equation, we'll get value of A as 5. So value of A is 5. Now first question is we need to find the value of A, B, C. Now A into B into C is
5 into 8 into 12, which is 10 into 4 into 12, 480, and that's your option D. Now the next question is, we need to discuss nature of roots of this equation. So for this, we'll calculate D, which is b square minus 4ac. Now b square is 64 minus 4ac is 4 into 12 into 5 minus 240, which is less than 0. So roots are imaginary. And it says, if ABC are roots of this cubic equation, then find the value of R. Now basically, if we write S2 for this equation, then AB plus BC plus CA, it is equal to R. So this R will be 12 into 8, 96 plus 12 into 5, 60 plus 5 into 8, 40, and there will be 196, and that's your option B. So correct options are D, C and B. Now here the question is, if A1, A2, A3 they are in AP, A2, A3, A4 they are in GP, and A3, A4 and A5 they are in HP, then A1, A3 and A5 are in. Now what we'll do is, we'll start from here. We know that A2, A3 and A4 they are in GP. So what we'll do is, we'll choose them as A3 by R, A3 and A3R. Now it says A1, A2 and A3 they are in AP, whereas A3, A4 and A5 they are in HP. Now if they are in AP, then 2 times A3 by R, it is equal to A1 plus A3. So we'll get A1 as A3 into 2 by R minus 1, or it is A3 into 2 minus R upon R, and this is our first result. And from the condition of HP, we can write 2 upon A3R, it is equal to 1 upon A3 plus 1 upon A5. So we can write 1 upon A5 will be equal to 1 upon A3, 2 upon R minus 1, and will be 2 minus R upon A3R, or basically A5 is equal to A3R upon 2 minus R, and that's our second result. Now it says A1, A3 and A5 they are in what? So we need to find A1, A3 and A5. Now A1 actually is A3 2 minus R upon R, then we have A3, and A5 is A3R upon 2 minus R. Now if we multiply them, we'll get A3 square. So basically these three numbers they are in GP, and that's your option B. Now the question is, if A, A1, A2, A3, A2n minus 1B are in AP, A, B1, B2, B3, B2n minus 1, B are in GP, and A, C1, C2, C3, C2n minus 1B they are in HP, where A, B are positive, then the equation A n x square plus B n x plus C n equals to 0 has its roots. Which of the following is correct? Now if you look at this first series, which is A, A1, A2, A, 2n minus 1 and B, we know that this AP has odd number of terms. So its middle term, it will be equal to arithmetic mean of terms equidistant from the beginning and end. So we can write A plus B by 2, and it will be equal to its middle term. Now total number of terms in this series is, so total number of terms in this series is 2n plus 1, and middle term will be n plus 1 term. Now this actually starts from 0, so its middle term will be an. So from here we can write an equals
a plus b by 2. Now we are given that a, b1, b2, b2n minus 1, b, they are in GP. If they are in GP, then their middle term bn will be equal to the geometric means of terms equidistant from beginning and end. So bn is equals to under root ab, and the same way a, c1, c2, c2n minus 1 into b, they are in HP, then their middle term Cn will be 2ab upon a plus b. Now we know that an, bn, cn, they themselves are in GP. So basically we'll have bn square equals an into cn. Now if we look at this equation, its discriminant will be bn square minus 4 ancn, and ancn is bn square, so it will be minus 3 bn square, which is less than 0. That means roots of this equation are imaginary, and that's your option C. Now here the question is, if ABC are in GP and APQ are in AP such that 2A, B plus P, C plus Q, they are in GP, then common difference of this AP is. Now if ABC are in GP, we know that B square equals AC and APQ are in AP. That means 2P equals Q plus A. And we are also given that 2A, B plus P and C plus Q, they are in GP. So that means B plus P square, it is equal to twice A into C plus Q. Now what we'll do is, we'll subtract first from third, then we can write P square plus 2BP and L be equal to AC plus 2AQ. Now AC is nothing but B square. We can make it a quadratic in B, so we can write B square minus 2BP, and then it will be minus P square plus 2AQ equals 0. Now from here we can write B as 2P plus minus under root of, now this is 4P square minus 4 and then minus P square plus 2AQ whole divided by 2. We'll cancel this 2. So we'll get this B as P plus minus, and here will be under root of 2P square, and then we'll have minus 2AQ. Now we know that 2P is Q plus A, so we'll multiply both sides with 2. We can write 2B equals 2P plus minus under root of 2 into 2P square minus 8AQ. Now 2P is Q plus A, so it will be 2B, and this is Q plus A plus minus under root of 2 Q plus A whole square minus 8AQ, or we can write 2B equals Q plus A plus minus, we'll take root 2 common, and then it will be A plus B whole square minus 4AB, and that will be A minus B whole square. There will be root 2 A minus Q. Now the question, A, P and Q, they are in AP. Now if the common difference of this AP is D, then basically Q minus A will be equal to 2D. So we can write 2B, and this is 2D plus 2A plus minus root 2, and this q minus a will be plus minus 2d. So it won't make a difference. So we can cancel this 2. Then we'll get b minus a. It is equal to d 1 plus minus root 2, or this common difference will be b minus a upon 1 plus minus root 2. Now if we take plus sign, then we get b minus a upon root 2 plus 1. We'll multiply and divide with root 2 minus 1. So it will be b minus a into root 2 minus 1. And if we take minus sign, then we can write b minus a upon 1 minus root 2. We'll multiply it with 1 plus root 2 and then 1 plus root 2. Now this is minus 1. So we'll get a minus b into 1 plus root 2. So the correct options are B and D. Now the question is, for the series 21, 22, 23 up to k minus 1 and k, the AM and GM of first and last numbers exist in the given series. If k is a 3-digit number, then k can attain how many values? Now, if we look at their arithmetic mean will be 21 plus k divided by 2. And since this series is a series of natural numbers, this a, it must be a natural number, and will be a natural number if this k, it is an odd number. So this k, it is odd natural number. So its arithmetic mean will exist in this series if k is odd. So that's our first condition. Now if we write their geometric mean will be under root of 21 into k. Now this again should be a natural number, and will be a natural number if k is of the form 21 into a square, where a is a natural number, then its geometric mean will be 21 into a, which will lie in this series. So this k, which is 21 into a square, it must be an odd number, and it should be of the form 21 into a square, and it is given that it's a 3-digit number. So it's a 3-digit odd number. Now we know that 21 into 9 is a 3-digit number. If a equals 1, it is not a 3-digit number. So we'll consider a equals 3. If we take a as 3, then this k will be 21 into 9. So this is 189, which is a 3-digit odd natural number. So this is one possibility. If we take a equals 5, we'll get k as 21 into 25, 525. This is also acceptable. And if we take a as 7, we'll get k as 21 into 49, and it will be 1029, which no longer is a 3-digit number. So there are only 2 values of a possible, and therefore we'll have only 2 values of k. So answer to this question is 2 values, and that's your option C. Now here the question is, suppose log b1, log b2, log b101 are in AP with the common difference log 2. Now if log b1, log b2, log bn, they are in AP with common difference of log 2, then essentially b1, b2 and bn, they are in GP with common ratio 2. Now it says, suppose a1, a2, a101 are in AP such that A1 equals B1 and A51 equals B51. Now we have defined two series. T is B1 plus B2 up to B51 and S is A1 plus A2 up to A51. Now we need to find inequality relationship between S and T and A101 and B101. Now T is sum of 51 terms of a GP. So this T is basically B1. Now R is 2 to the power 51 minus 1 upon 2 minus 1. So that's your T. Now this AP, A1 is B1 and A51 is B51. So we can write B51 is B1 plus n minus 1 into D. So its common difference will be B51 minus B1 divided by 50. So this sum, it will be 51 by 2 A plus 51 and A1 is B1. So it will be 51 by 2 B1 plus B51 and B51 is B1 to the power 50. So we can take B1 common. So there will be 51 B1 by 2 1 plus 2 to the power 50. Now this is B1 into 25.5 and this is 2 to the power 50 plus 1. Now clearly this value is greater than 2. So it will be greater than B into 2 to the power 51 minus 1. So clearly S, it is greater than T. So result is sum of an AP is greater than sum of GP. So S greater than T. Now we need to find relationship between A101 and B101. Now clearly B101 is B1 to the power 100, whereas A101 will be B1 plus 100 and this D is B1 to the power 50 minus B1 whole divided by 50. Now this is 2. So it is B1 to the power 51 minus 1, which is lesser than B1 to the power 100. So A101, it is less than B101. So answer to this question is S is greater than T and A101 is less than B101. That means the correct option is this option B. Now here the question is, let A1, A2, A3 be a sequence of positive integers in AP with common difference 2. So we have an AP with terms A1, A2, A3 up to AN, and then also the series continues, and given that its common difference is 2, and we are given the sequence of positive integers B1, B2, B3 in GP. So we have this series B1, B2, B3 up to Bn, and this series terms are in GP. So first series terms are in AP and the second series terms are in GP with common ratio 2. And it says if their first terms are equal and they're equal to C, then number of all possible values of C for which this equality, the equality is 2 times A1 plus A2 plus AN, it is equal to B1 plus B2 to Bn holds for some positive integer n. Now this is sum of first n terms of an AP. So this is 2 times n by 2, 2a, and a here is C plus n minus 1 and common difference is 2, and this is sum of GP. So it will be a r to the power n minus 1 upon r minus 1. Now here 2 and 2 will cancel. So we'll get this as 2nc plus 2n into n minus 1, and this is equal to c into 2 to the power n minus 1. Now we can write this c as 2n into n minus 1 upon 2 to the power n minus 2n minus 1. Since c is a1, b1, which are sequence of positive integer, that means this c, it is a positive integer. So we are looking for positive integral value of c, and since in the denominator we have 2 to the power n, we know that denominator is going to grow faster than the numerator. So there will be some value of n after which numerator will be less than denominator. Then we cannot have a value of c. So it will give us some sort of upper limit of n. So we are looking at condition where 2n n minus 1, it should be greater than or equal to 2 to the power n minus 2n minus 1. Now here minus 2n will cancel, so we'll get 2 to the power n will be less than or equal to 2n square plus 1. Now 2 to the power 5 is 32, and this is 25 into 2, that's correct. 2 to the power 6 is 64, and this is 72, that's also correct. And so 2 to the power 6 is less than 2 into 36 plus 1, this is 64, and this is 73, this is true. Now 2 to the power 7 is 128, and this is 49 square, 98 plus 1, 99. So n should be less than or equal to 6, and clearly n should be greater than 1. So n can take the values between 2 and 6. Now in between 2 and 6, we need to find the values of n, for which we will get the value of c as positive integer. Now if we put n as 2, we will get c as 4 upon 4 minus 1. We do not need a negative value. If we put n as 3, we will get the c as 6 into 2, and this is 2 to the power 3, 8, minus 6, minus 1, and that will be 12. So we have a positive integral value at n equals 3. If we put n as 4, we will get this c as 8 into 3, and this is 16 minus 8 minus 1. So it will be 24 by 7, not an integer. If we take n as 5, we'll get this c as 10 into 4, and this is 2 to the power 5, 32. 32 minus 11 is 21, which is again is not an integer. And for n equals 6, we'll get this c as 12 into 5, and this is 2 to the power 6, 64, minus 12 minus 1. So there will be 60 upon 53, which again is not an integer. So the only integral value of c is when the value of n is 3. So there is only one positive integral value possible for c. So answer to this question is 1. Now the question is, if a, b, c are in GP, that means b square equals ac, then the equations ax square plus 2bx plus c equals to 0 and dx square plus 2ex plus f equals to 0 have a common root, then d upon a, e upon b, f upon c are n. Now if we look at this first equation, if we write its discriminant, it will be 4 b square minus ac, and since b square equals ac, discriminant is 0, that means this equation, it has got equal roots. Now if it has equal roots, we know that sum of roots will be 2 alpha, will be minus 2b by a, so alpha is minus b by a, and since this is a common root, it will satisfy the second equation, so we can write d b square by a square minus 2 be by a plus f equals 0. Now we know that b square is ac, so we can write
AC by A square minus 2 EB by A plus F equals 0. Now here A and A will cancel. Now we'll divide everything with C also. We can write D upon A minus 2 EB upon AC plus F upon C equals 0. Now AC is B square and B will cancel. So we'll write D upon A minus 2 E upon B plus F upon C equals 0. Or we can write twice E by B. It is equal to D by A plus F by C, which is D by A, E by B and F by C. They are in AP. So answer to this question is this option A. Here the question is, let A1, G1, H1 denote the arithmetic, geometric and harmonic means respectively of two distinct positive numbers. So let the two numbers be A and B and such that A is greater than B. Now we know that AM, GM and HM, they lie between the two numbers and their arithmetic mean will be greater than their geometric mean and will be greater than their harmonic mean and will be greater than B. Now it says, let AN minus 1 and HN minus 1 has arithmetic and geometric means as AN, AGN and AHN. Now we know that AN minus 1 will be greater than HN minus 1 since AM is always greater than HN, and for these numbers their AM is AN, GM is GN and HM is HN. Now we know that AN will be greater than GN and GN will be greater than HN, and these means they will lie between AN minus 1 and HN minus 1. So from here we can write AN minus 1 will be greater than AN, will be greater than GN and will be greater than HN and it will be greater than HN minus 1. So these are extreme values A and B, and all these three means they lie between them. Here if we continue the sequence, we can write A1 will be greater than A2 will be greater than AN and HN will be greater than HN minus 1 will be greater than H2 will be greater than H1. So from here we can say our result is A1 should be greater than or equal to A2 and H1 should be less than H2. So 56 is A and 57 is B. Now AN is arithmetic mean of this. So AN will be AN minus 1 plus HN minus 1 by 2 and GN will be AN minus 1 HN minus 1 to the power 1 by 2 and HN will be twice AN minus 1 HN minus 1 upon AN minus 1 plus HN minus 1. Now if we multiply these, we can write AN into HN, AN minus 1 and HN minus 1. Now this is GN square. This is GN minus 1 square. So from here we can say G1 must be equal to G2 must be equal to GN. That means this option C is correct. So the correct options are C, A and B.